Supersonic motion, as the name suggests, deals with motion that is faster than the speed of sound in a medium. So you can imagine a plane moving, and if the plane is moving slower than the speed of sound in air, for example, then waves travel away from the plane, right? The waves move faster than the plane does, so the plane can't catch up to all of its waves. In the case of supersonic motion, though, a plane is moving faster than sound waves can travel, and so the sound waves in front of the plane start to pile up, and they form what is called a shock, this thin structure I've drawn there. Now, I haven't worried too much about the shape of the shock. You can imagine that maybe it wouldn't be right at the edge of the needle at the end of the plane, but there is a shock structure that forms, and that represents air that would form waves, but it doesn't have time to propagate as a wave because it keeps getting shoved from behind by the plane. Okay. So the first time that somebody on the ground would find out about this plane, assuming that they weren't looking at it, light travels faster than sound, but if they were sitting there looking in the other direction, then the plane has to get there before the person finds out about the plane, and the way that they find out is through a sonic boom. So the plane is generating a shock, that shock wave hits the person, hopefully the shock wave isn't that strong and it's just a loud noise, nothing that would hurt them. That's when they find out that there's a plane there, because the fastest that information can travel by sound through the air is at the speed of sound, unless you're shoving it ahead in a shock. If you're moving in a shock, then you can't possibly have waves in advance of the shock deliver information about what's moving around. To further illustrate the difference between subsonic and supersonic motion, I conducted a numerical simulation of fluid moving around a sphere. On the left side, we're going to have fluid moving around a sphere subsonically, so slower than the speed of sound in the fluid. On the right side, we'll have fluid moving around supersonically, so faster than the speed of sound in the fluid. What is visualized here, the color is density, so it's sort of a light blue. It will become brighter and whiter at higher density and darker and dimmer at lower density. Those arrows represent the velocity vectors, so initially the flow is not in perfect equilibrium. You can see some of the velocity is pointing right at the sphere, so it will have to relax into a steady flow. Those will change a little bit, but you'll see more dramatic differences in the supersonic case than the subsonic. So let's start with subsonic. On the left, all right, the flow has started. You can see, as I said, the arrows rearrange themselves. There's not a huge difference in density on the left side and the right side of the sphere, though. You can see a little tiny wave that went out just as the system adjusted, but that's it. Generally speaking, the color is about the same. Now, what about the supersonic case? Well, here you can see a shock forms on the front side of the sphere. Remember, the flow is going from left to right as the velocity vectors indicate, so it's forming a shock ahead of the sphere, from the sphere's perspective. Behind it, you can see that the density actually overall has decreased, just because it's forming a wake behind it, where stuff hasn't quite had time to catch up because it's moving so fast. You can also see there's a little feature that looks like the Starship Enterprise behind the sphere. I didn't have anything to do with that, just came out of the data. Okay, so that's the difference between subsonic and supersonic flow around a sphere. You can imagine another context in which you might encounter such flows, which have to do with explosions. Now, they don't all have to be explosions like weapons going off. There are astrophysical explosions like supernova explosions when stars explode, for example. And all I did in this set of simulations was to construct a high-pressure region in the middle of a computational grid and just let it evolve. We know that won't be in hydrostatic equilibrium, right? If you just have this region of really high pressure, you can imagine that something just exploded to generate this, and now I'll let the system evolve. On the left side, you'll be able to follow the density. On the right side, you'll be able to follow the pressure. So watch what happens when this region explodes. So it explodes and forms a shock. I put in enough initial energy that there is a shock wave forming out from the center. And the interesting thing about this, that is different from the two cases we just saw, is that you don't have a solid object generating the shock. So it's not like there's a plane flying through or a sphere that's moving relative to a fluid so fast that it's forming the shock. The shock is formed simply by other parcels of fluid trying to move faster than the speed of sound, and they're forced to because there was so much energy in the initial explosion. So you can see two interesting things. You can spot the shock both in density and pressure, and in the density in particular, you can see that just as there's a density enhancement for the shock structure, there is also a density decrement, a drop in the middle of the structure. Well, mass is conserved, so the mass had to come from somewhere. If you increase the density in one place, you have to lower it someplace else, and you end up lowering it in the middle of this shock wave. So if you have a really big explosion, the center might actually have a much lower density after the shock wave has passed through, just because all the air is rushing to get away from the center of the shock. I conducted one more version of this simulation in which I also added gravity. So you can imagine if you drive the density down, then suddenly the system becomes buoyant. Now this is zoomed out a little, so the explosion initially is not quite as large. There's a little white dot on the pressure that's about to explode, and here it goes. And once the density is reduced as a result of this shock being formed, as a result of this explosion, you can see the buoyant region rises up. This may be familiar to you if you've ever seen pictures of atomic bomb tests. There's a mushroom cloud produced, and it's caused by buoyant rising of low-density air. It also happens astrophysically. There are structures that erupt within our own galaxy, and they shoot up out of the plane of the galaxy as a result of having lower densities up there. They buoyantly rise.